In the following problem, we're asked we're asked a series of questions, but it really comes down to the fact that this person in the chair is being swung around in a circle from the end of a rope. He's sitting in a chair. We're given the length of the rope. We're given the length of this arm, which is from the pivot point. And obviously, as this thing spins around, the person is going to travel in a circle. Okay, the first question here was we're asked to find the radius of the circular path of the rider. Well, this is rather quite simple. If you look at the person, I've just created this right angle triangle right here, and looking at the two distances that we need this 3 meters for this arm, and we need to add this distance, which we can get from the right angle triangle. So the radius of the circle that he travels on is just 3 meters plus that component, which is 5 times sine of 30 degrees. So that's this component here is 5 times sine of 30 degrees, and this equals 5.5 meters. So that's the answer to part A. Part B I've actually already done as well. Part B is right below here. We're asked to draw the free body diagram for the rider. So if we treat the rider as a point mass at the origin on this coordinate system, there are two forces acting on him. There's the tension in the rope, as well as the force of gravity. Now, in this case, we're ignoring any kind of drag due to air. This is a magical physics land. So once again, two forces, the tension and the force of gravity, and we have a net force which has to be towards the center of the circle. So in this case, it's in the negative x direction. So this is our free body diagram. That's part B. So part C, we're asked to solve the problem to find the speed of the rider. In order to solve the problem, we should turn to Newton's second law. So we're on part C. So from Newton's second law, so remember that's the net force as a vector is equal to mass times acceleration as a vector, and we can in fact just consider the Newton's second law in component form. So let's consider the sum of the components of the forces in the x direction. That gives us, there's a component of, actually it's just the component of tension, which is that side right here. So this side of this right angle triangle right here is the component of the tension force in the x direction. So that's given by Tx. And in terms of sine and the magnitude of the tension, sorry, that's not Tx. Let's go back and erase this. It's, with our notation, it's just the tension force in the x direction, and that's equal to negative T times sine of 30 degrees. And that is going to equal to mass times the acceleration in the x direction. Okay, let's leave that for now, and let's turn to the components of the forces in the y direction. In the y direction, we have two components. There's the component of the tension force in the y direction. That's this side of the right angle triangle. And there's the force of gravity. So writing this out in component form, we have Fty plus Fgy, and that's equal to mass times Ay. And one thing to note is this person isn't accelerating in the y direction, just in the x direction. So the right-hand side of Newton's law, a second law, is 0. Alright, I'm going to deal with this second equation here. I'll call it equation 2. The other one we'll call equation 1. So from equation 2, we can substitute in for the components. So the component of the tension force in the y direction is the magnitude of the tension force times cosine of 30 degrees. And then we subtract the component of, when we substitute in for the y component of gravity, it's just negative mg, and this has to equal 0. So, solving for the, there's a subscript issue here. That's not Fy, that's Ft. So solving for the tension force, we get mg over cosine of 30 degrees. All right. Now, we can now turn to equation 1. We can write from equation 1, we get the following. We have tension. Again, I'm messing up the notation here, so it's F sub t. So we have F sub t we know is mg cosine 30 degrees. There's a negative sign here because it's in the negative x direction. And that's equal to mass times the acceleration in the x direction. And I'm making a lot of mistakes here. I forgot the sine 30. So this, going back here, this expression is just this one here, where I've substituted in for F sub t. Okay. We know something about that acceleration. That acceleration is radial acceleration, and it's in this particular instant, it's in the negative x direction, so we can write this as negative v squared over r. Okay, it's a bit of a mess here, but the m's cancel, and I end up with, well, the negative signs cancel, and the sine and the cosine combine to give tan of 30 degrees, and that's equal to v squared over r. And so finally we get an expression for the velocity, or sorry, the speed rather, and that's just g times r times tan theta. And I evaluated this, actually I haven't evaluated it, but let's just leave it like that for now. Okay, so that is an expression for the speed of the rider. Now, the last question is, how long does it take to make one complete revolution? So that's part D right here. So, in one revolution, this rider travels the circumference of the circle. So the circumference of the circle is just 2 pi times r. And we know that the period, capital T, is equal to the circumference over his speed, v. So the circumference was 2 pi r, and the speed we found to be the square root of gr tan theta. Or, well, tan theta, but in our case, theta is 30 degrees. Alright, we've calculated r above. R we found to be 5.5 meters. That's this quantity here. G is the usual 9.8. We have tan theta. We can plug in everything into this and get a number. So the period of the motion is 6.19 not meters, but seconds. So it takes 6.19 seconds to make one complete revolution. You could go back and substitute in for the radius here and g and get an expression for velocity as well. Okay, that's all.